An electromagnet is a type of magnet in which the magnetic field is produced by an electric current. The magnetic field disappears when the current is turned off. Electromagnets usually consist of a large number of closely spaced turns of wire that create the magnetic field. The wire turns are often wound around a magnetic core made from a ferromagnetic or ferrimagnetic material such as iron. The magnetic core concentrates the magnetic flux and makes a more powerful magnet. The main advantage of an electromagnet over a permanent magnet is that the magnetic field can be quickly changed by controlling the amount of electric current in the winding. However, unlike a permanent magnet that needs no power, an electromagnet requires a continuous supply of current to maintain the magnetic field. Electromagnets are widely used as components of other electrical devices, such as motors, generators, relays, loudspeakers, hard disks, MRI machines, scientific instruments, and magnetic separation equipment. Electromagnets are also employed in industry for picking up and moving heavy ironed objects such as scrap iron and steel. History. Danish scientist Hans Christian Ørsted discovered in 1820 that electric currents create magnetic fields. British scientist William Sturgeon invented the electromagnet in 1824. His first electromagnet was a horseshoe-shaped piece of iron that was wrapped with about 18 turns of bare copper wire. The iron was varnished to insulate it from the windings. When a current was passed through the coil, the iron became magnetized and attracted other pieces of iron. When the current was stopped, it lost magnetization. Sturgeon displayed its power by showing that although it only weighed 7 ounces, it could lift 9 pounds when the current of a single-cell battery was applied. However, Sturgeon's magnets were weak because the uninsulated wire he used could only be wrapped in a single spaced-out layer around the core, limiting the number of turns. Beginning in 1830, U.S. scientist Joseph Henry systematically improved and popularized the electromagnet by using wire insulated by silk thread inspired by Schwager's use of insulated wire to make a galvanometer. He was able to wind multiple layers of wire on cores, creating powerful magnets with thousands of turns of wire, including one that could support 2,063 pounds. The first major use for electromagnets was in telegraph sounders. The magnetic domain theory of how ferromagnetic cores work was first proposed in 1906 by French physicist Pierre-Ernest Weiss, and the detailed modern quantum mechanical theory of ferromagnetism was worked out in the 1920s by Werner Heisenberg, Lev Landau, Felix Bloch and others. Uses of electromagnets. A portative electromagnet is one designed to just hold material in place. An example is the lifting magnet. A tractive electromagnet applies a force and moves something. Electromagnets are very widely used in electric and electromechanical devices, including motors and generators, transformers, relays, including reed relays originally used in telephone exchanges, electric bells and buzzers, loudspeakers and earphones, actuators, magnetic recording and data storage equipment, tape recorders, VCRs, hard disks, MRI machines, scientific equipment such as mass spectrometers, particle accelerators, magnetic locks, magnetic separation equipment, used for separating magnetic from non-magnetic material. For example, separating ferrous metal from other material in scrap. Industrial lifting magnets, magnetic levitation, induction heating for cooking, manufacturing, and hypothermia therapy. Simple solenoid. A common tractive electromagnet is a uniformly wound solenoid and plunger. The solenoid is a coil of wire, and the plunger is made of a material such as soft iron. Applying a current to the solenoid applies a force to the plunger and may make it move. The plunger stops moving when the forces upon it are balanced. For example, the forces are balanced when the plunger is centered in the solenoid. The maximum uniform pull happens when one end of the plunger is at the middle of the solenoid. An approximation for the force F is where C is a proportionality constant, A is the cross-sectional area of the plunger, N is the number of turns in the solenoid, I is the current through the solenoid wire, and L is the length of the solenoid. For units using inches, pounds force, and amperes with long, slender solenoids, the value of C is around 0.009 to 0.010 psi. For example, a 12-inch long coil with a long plunger of 1 square inch cross-section in 11,200 ampere turns had a maximum pull of 8.75 pounds. The maximum pull is increased when a magnetic stop is inserted into the solenoid. The stop becomes a magnet that will attract the plunger, but it adds little to the solenoid pull when the plunger is far away, but dramatically increases the pull when they are close. An approximation for the pull P is here. L is the distance between the end of the stop and the end of the plunger. The additional constant C1 for units of inches, pounds, and amperes with slender solenoids is about 2,660. The second term within the bracket represents the same force as the stop-less solenoid above. The first term represents the attraction between the stop and the plunger. Some improvements can be made on the basic design. The ends of the stop and plunger are often conical. For example, the plunger may have a pointed end that fits into a matching recess in the stop. The shape makes the solenoid's pull more uniform as a function of separation. Another improvement is to add a magnetic return path around the outside of the solenoid. The magnetic return path, just as the stop, has little impact until the air gap is small.